Okay, we're going to start here with question 16, I guess. So we have a function where the top function is x cubed plus 2, and we use that for x being greater than or equal to 0. So here's the top function. The bottom function is used for values of x that are less than 0. This is on the bottom. So as we can see with the first question, when x is greater than 0, or I should say as x goes to 0 from the right, they're talking about using positive x values. Because you're going to 0 from the right, all the x values are positive. So for positive x values, we have to use the top function because it's defined for values of x being greater than or equal to 0. So this would be 0 cubed plus 2. We just plug in that value for x into that function here and do our arithmetic. And that's going to become 0 cubed would be 0 plus 2. And then that limit will be simply the value 2. Okay. For 17, x goes to 0 from the right. That means x is actually less than 0. So for values of x that are less than 0, your piecewise function says use the bottom piece. In other words, plug in your x value down here, and now you'll get 2 minus 0. And 2 minus 0 is the value 2. And so since the left-handed limit equals the right-handed limit, they're both 2, we can say that the limit as x goes to 0, irregardless of the direction, left or right, is the value 2 because it's the same. So that's what this means here. Both the left and the right are equal to 2. I want to note something here, that the value of the function as well at 0 is found by using the top function because it's defined for values of x that are greater than or equal to 0. So that would be 0 cubed plus 2, which is 0 plus 2, which is going to be 0. So there we go. Sorry, 0 plus 2 is 2. So the value of the function at 0 is equal to 2. And so just looking at this curve, looks like, yes, we can sketch this curve without picking up our pencil anywhere on that point, especially when x is 0. So they didn't ask this question, but we're going to note and say that this function f is continuous at x equals 0. And why? Because the limit as x goes to 0 of the function is the same as the value of the function. In other words, the limit is 2 and the value of the function is 2. So this is how we actually work with this piecewise function. Okay, I know we're just finding limits, but we're looking at this in terms of continuity as well. All right. Let's look at how to read this piecewise function. Now, you have a rational function on top here that's used when x is greater than or equal to -1. However, there's a problem here with this. The denominator could never be 0. So x plus 1 cannot equal 0. We'll set it equal to 0, solve for x, and we know x could not be the value -1. So this is going to be actually strictly greater than. We have to fill that value out. So the top piece is used for values of x that are bigger than -1. The bottom piece is used for values of x that are less than -1. So let's kind of indicate this here. And I think there's a little bit more going on. So we have top and we have bottom. If we look further here, we have x squared minus 3x minus 4 over x plus 1. If we simplify this rational, the top is factored as I believe this will be x minus 4 and x plus 1. Yes. So we can get rid of this portion here, and really your top piece is an x minus 4 here. So the top piece is really x minus 4, ladies and gentlemen. Yes. And that's why you'll see the line that you see in the curve here. But again, x could never be negative 1. So that's going to be very helpful because of the fact that when you try to look at the limit, as x goes to negative 1 from the right and the left here, this means going to negative 1 from the right means x is bigger than negative 1. X going to negative 1 from the left means x will be smaller than negative 1. So we have to know what piece we're going to use for the value of x being negative 1. So bigger than negative 1 is the top piece, which is really x minus 4. So we're going to plug in the negative 1 here for x. For the top, that's negative 1 minus 4, which gives us a negative 5. Okay. Now, as x goes to negative 1 from the left, these values of x are smaller than negative 1. So we're going to use that bottom piece, plugging in x being negative 1 here, and we get negative 1 plus 5 now. And that answer is actually negative 4. Okay. Yeah. So the limit as x goes to negative 1 does not exist because these aren't the same. Pointing this detail out to you guys. And I'm looking at the graph, and I'm thinking here, it looks like, is this the correct graph? The top graph of x minus 4 is correct. The bottom graph of x plus 5 is not correct. So, yeah, x plus 5 actually is not correct here. X plus 5, let me get something out here. Get a pencil. The y-intercept, oh, I'm sorry. X minus 4. Yeah, the y-intercept, the top graph, that looks okay for values of x bigger than negative 1. And the x plus 5, yeah, this graph here should go through this point with a positive slope as well. But really, at negative 1, we should have this over here. So this graph is wrong. We're going to have to fix that one here. Just so you know, there's a hole there. Yeah. And that's a positive 4, by the way. So it's pretty late. Found a typo. Apologize for that. Okay, find the typo in the graph. And really that's what it looks like. But I guess the most important thing to note about this is that at negative 1, this curve is not continuous. The value of the function at negative 1 is undefined. There is no point you can use here for that. -1, because you had to throw out -1 here. Could never divide by that 0 here. So you said x plus 1 equal to 0. So this is undefined. And so just to kind of reiterate those ideas of continuity, the function f is discontinuous at -1. We'll say not continuous. Okay. At x is -1. Why? Because the limit as x goes to -1 of the function is not equal to the value of the function at -1. The limit does not exist on that left side, and the value of the function is undefined. So, ladies and gentlemen, nope, those are not the same. These are not the same ideas. Okay? Just to kind of look at that picture in the correct graph here for this. All right. This is interesting because now we have 3 pieces. Got 3 pieces here. Your top piece is used for values of x that are less than 0. So we call this the top. The bottom piece down here, just this x cubed, is used for values of x that are less than or equal to 0. I'm sorry, less than or equal to 1, as it says here. And then we'll say the middle piece. This is in the middle here. I will use gray. We use this for these values of x between 0 and 1, but this is x will be, 0 is less than or equal to x. So this is called the middle piece. Maybe we'll just put a little m for middle. So we have to know how to read these pieces. The graph is over here. You guys can see these graphs here. So when you're saying what's the limit as x goes to 0 from the right, you're asking to use the positive x values, because for x going to 0 from the right, meaning those values are bigger than 0. X going to 0 from the left, meaning the x values are less than 0, and they're close to 0, but they're less than that. So you got to find what piece you're going to be using for each function here. So the key again is, can you read the piecewise function? So for the first limit, as x goes to 0 from the right, they're really talking about this portion right here. Okay, and you plug in that value of x there being 0, so that'll be 3 minus 0 now. So this will be 3 minus 0, which is the value 3. And then x going to 0 from the left, meaning you have negative x values. X is less than 0. So for x being less than 0, you got to use that top piece now. That's what they're talking about now. Plug in 0 here. And so you have 4 plus 0 squared now. So it's about, can you read your piecewise function? And then do some arithmetic. So, okay, the right-handed limit is 3. The left-handed limit is 4. These are not the same. So this limit does not exist at 0. So when you look at this general question, we know this does not exist. Okay, because the limits are different. Yes, they're both finite, but they're not the same. And, just to see if you're awake here on this one, the value of f, the function at 0 now, you got to use the middle piece, because that middle piece says use me when x is less than or equal to 0. So you plug in 0 in that middle piece now. So that will be 3 minus 0. So this answer is just simply 3. F of 0 is 3. All right. So, I mean, I could notate it down here. And it doesn't mean much in terms of being continuous, because you're looking at what's going on around 0 here. What's going on around 0 is what you see. This is known, by the way, as a jump discontinuity. And the reason it's a jump discontinuity is because when you sketch that curve, you got to jump to get back to this point or at 0. This is where x is 0. And so that's a very much a picture of a function that's not continuous at 0. So if they ask you, is this function continuous at 0, you can say, no, f is not continuous at x equals 0 because the limit as x goes to 0 of the function is simply not the same as the value of the function at 0, because the limit does not exist. We already seen that answer right here. And the value of the function is actually 3. So this is what I want to point out to you in detail. This portion does not exist. And this portion is just 3. So this is not the same. Function's not continuous at x is 0. This is the work you do. You don't have to sketch the curve. You just have to read your piecewise function and use your definitions. Okay, it's a jump discontinuity at that location. In fact, there's another jump discontinuity. We didn't ask you at x is 1, though. You know, the left-handed limit is 2. The right-handed limit looks like 1. Limit does not exist. The value of the function at 1 is 1. So I can find that out just by looking at this picture here. Okay, this is a picture of, again, another jump discontinuity, but this time it's at the value x is 1. All right, pretty fun. Is it at x is 1? Yeah. So I'm going to say this. So we're going to look at this here. I'm going to change this here to be x is 1, 25, 26, 27 now. Let's look at this picture at x is 1 now. Okay. So let's do the reading of this. As x goes to 1 from the right, x is bigger than 1. And as x goes to 1 from the left, x is smaller than 1. We have to know what pieces to use just by reading that piecewise function. So this is what this means. As x goes to 1 from the right, your values of x are close to 1, but they're bigger than 1. And as x goes to 1 from the left, the values of x are close to 1, but they're smaller than 1. Okay, for x being bigger than 1 now, let's go back and read this. What piece do we use when x is greater than 1? And I can see another issue right here. That should be greater than or equal. All right, we're going to have to fix a couple of those typos on this question here. Okay, so fix that there, that typo. X is greater than or equal to 1. Now, we're going to use the bottom piece there. So this means this is going to be 1 cubed. And 1 cubed is the value 1. Now, the limit as x goes to 1 from the left, that's x is smaller than 1. And for x being smaller than 1 now, I want you guys to see it right here. This is the piece you use. So you're going to plug in 1 here for x. So that'll be 3 minus 1. Okay. 3 minus 1 now is the value 2. All right. And so what we know now, again, the limit as x simply goes to 1 does not exist because these two limits are different. You know, the notation, if you wanted to see notation there, the limit as x goes to 1 from the right of the function is not the same as the limit as x goes to 1 of that function. These are not the same because 1 is not the same as the value 2. All right. But let's take a look at how to read this one again. What's the value of the function at 1? Well, the value of the function now, when x is 1, is 1 cubed, because we use this bottom portion for x being greater than or equal to 1. And that's going to be the value 1. Okay? And it's all illustrated in this picture. The right-handed limit is 1. The left-handed limit is 2. The value of the function, the reason they have that dot there is because you can use that portion of the curve, the x cubed, when x is 1. Because that's how it's defined here. All right. And then similarly, you can say f is not continuous, even though they never asked it in the exercise, at x equals 1. Why? Because the limit as x goes to 1 of the function is not the same as f of 1, because does not exist was the limit, and f of 1 we know is the value 1, and those two ideas are not the same. That's what we're saying. All right. Okay, let's see what's going on with this question here. Remember, we got to know how to read this. The top portion of x minus 3 is used for x being less than or equal to 1. The middle portion of negative 2x squared is used for 1 between 1 and 5. Do not include 1 or 5. And then the bottom portion here is used for x being greater than or equal to 5. So we just simply have to know how to read a piecewise function. And then with the knowledge now that x is going to 1 from the right simply means those values of x are close to 1, but they're actually bigger than 1. And going to x from the left means those values of x are close to 1, but they're smaller than 1. And then that's the key to knowing what piece to use again. So x is bigger than 1, we know we got to use the middle piece. Because x is bigger than 1 is really right here. So we just simply plug in a 1 here for x, and that'll be negative 2 times 1 squared. Negative 2 times 1 squared by order of operation is negative 2 times 1, which will equal negative 2. All right. So this is the right-handed limit. It's negative 2. The left-handed limit, though, x is smaller than 1. So let's see, what piece do we use for x being smaller than 1? Oh, we use the top piece here. Because they're pretty much saying use that for x is less than or equal to 1. So I'm going to plug in 1 here for the x minus 3. So I get 1 minus 3 is also negative 2. Okay, so then that limit is going to equal negative 2 at x is, well, as x approaches 1. Because both the left-handed limit and the right-handed limit are the same. That's happening at 1. And if you look at the picture, that's definitely happening here. Left-handed limit is equal to the right-handed limit. Notice the value of the function at 1. We use the top piece, which would be 1 minus 3, which is negative 2. It's the top piece because we use the top for x being less than or equal to 1. So that says the function's continuous, ladies and gentlemen. at 1. So I'm just going to label it right here. Well, we can label it down here. F is continuous at x equals 1 because the limit as x approaches 1 of the function is the same as the value of the function at 1. In both cases, this is negative 2 equals negative 2. All right. Okay, they never asked that question, but that's what's happening around this 1 here. And now they're going to ask you another question. Hey, what's happening around 5? So if x is going to 5 from the right, we know that means the values of x are close to 5, but they're bigger than 5. And as x goes to 5 from the left, they're close to 5, but they're smaller than 5. We just have to know how to read our piecewise function and then do our direct sub. So for x being bigger than 5, go back over here. And we know, again, we got the top piece, the middle piece, and then the bottom piece. For x being bigger than 5, we got to use that piece down there because that's x is greater than or equal to 5. Use the bottom piece. So we're going to plug in 5 here. So that's going to give us the square root of 5 minus 1, the square root of 4, and that limit value is 2 when we use our direct substitution. Similarly, when x is smaller than 5, you say, what do I use when x is smaller than 5? You're going to use right here, x less than 5. So you're going to plug in 5 for x over here. And that'll be negative 2 times 5 squared now. So negative 2 times 5 squared is negative 2 times 25, which is actually negative 50. And I guess that is in the picture. That's what I was looking at. Okay. Well, the left-handed limit is not the same as the right-handed limit, so this limit does not exist. It means the limit as x goes to 5 does not exist by definition. And because of that, around 5, we know f of 5, though. You say, which piece do I use when x is 5? Well, you use the bottom piece because they say use that when x is greater than or equal to 5. So that's the square root of 5 minus 1, which would be the square root of 4, and that answer is a 2. They didn't ask this question, but be prepared for that. Our function f is not continuous at x is 5 because the limit as x goes to 5 of that function is not the same as f of 5 because does not exist is not the same as looks like that was 2, right? Yeah. Okay. And again, you guys can look at the picture on it. The picture's fine. So that leaves us up to what we've done earlier now, before. Let's do a very similar piecewise function and call it a night here. This is x plus 1 over the absolute value of x plus 1. So I want to point out to you, we're probably going to need some paper here. Whenever you deal with the absolute value in piecewise functions, right? X plus 1 over the absolute value of x plus 1. Your denominator could never be 0. That means this whole thing can't be 0. So you have an absolute value equation to solve And what that means is that implies that the between the absolute value sign has to be equal to 0. And solving for x by subtracting 1, we find x equals -1. That's the value that was thrown out of our domain. We can't have that. So x cannot be the number -1, just to kind of start this off. So use what we talked about in terms of the definition of a piecewise function, meaning the absolute value of anything is that thing when it's greater than or equal to 0, or it is opposite when it is less than 0. It's defined piecewise. Let's make sure there's a negative there. So when we put this together, you get x plus 1 divided by the absolute value of x plus 1. By definition is x plus 1 over x plus 1 when the x plus 1 is greater than or equal to 0. It is x plus 1 over minus x plus 1 when the x plus 1 is less than 0. And let's move this around here so you guys can see this very clearly. Now the rest is algebra because anything divided by itself is 1. Anything divided by itself where the denominator is negative, this will be -1. And then solving for x here by subtracting 1 now, we simply get the definition of this function is +1 when x is greater than or equal to -1. It is -1 when x is strictly smaller than -1. So this is how we get a handle on this piecewise function. Pre-calculus, ladies and gentlemen. Now remember you said, but wait a minute, x could never be -1. That's right, so we have to remove the equal part. So don't forget, whenever you have piecewise, you must use these here. Got to use that definition here. And so that's really how the function's defined. It's not defined, and I want you guys to note here that the value of the function at -1 is undefined. It's not even defined, okay? So that means there'll be a hole in the graph at -1, and that's pretty much why you see what you see. This is the graph on the top. That's the constant function 1. The bottom is the constant function -1. So it goes back to your graphing skills from algebra pre-calculus. So now you say, okay, let's do the limit questions. Okay, so if the limit is x goes to -1 from the right, means x gets close to -1, but x is actually larger than -1. You're going from the right, okay? As x goes to -1 from the left, you're getting close to -1, but these values of x are smaller than -1. So that's going to determine which ones we use, which piece. So for the right-handed limit now, x goes to -1 for the right, to the right, x is bigger than -1. That means we use this piece right here. The top piece, this is used when x is bigger than -1. That means it's 1. So it's a constant function. This is the value 1. I'll keep it orange, I guess. And then the bottom piece, you say, what do I use when x is smaller than -1? You're going to use that bottom piece. You say, why? Because that's how it's defined. Use -1 when x is smaller than -1. So it's going to be -1, the constant value. And again, what we certainly know is that these two values are not the same. So that limit does not exist. Okay? Irregardless of the approach here, this is just the limit as x goes to -1 does not exist. And we just got through saying that the value of the function at -1 is undefined. So I just want to say this function is not continuous at, very much not continuous at x is -1. Why? Because the limit as x goes to -1 of the function does not equal f of -1. So does not exist is not the same as saying undefined. Those are two different things. And you can actually see it in the picture. There's a jump discontinuity. When you sketch that curve, you had to jump around x is -1. There you go. So, we're going to maybe just do one more for fun. I apologize to you guys. One more for fun. It has the absolute value. Now, if you look at this curve, this is a nice, smooth, continuous curve. But how do we answer these questions without it? All right. Notice they gave us in this. Let's just do this one tonight, and then we'll call it a day. See that absolute value of x? Because you have the absolute value of x, you want to remember to use the piecewise definition. It is x when x is greater than or equal to 0. It is opposite x when x is less than 0. That's what you're going to use. So you say, okay, 2 absolute value of x plus 7 now will be defined piecewise. It's 2x plus 7 when x is greater than or equal to 0. And then it's 2 times, let's get some space here, 2 times that minus x plus 7 when x is less than 0. So you can do a little bit of simplification of this function. The top is just 2x plus 7. That's the top curve when x is greater than or equal to 0. The bottom will be negative 2x plus 7. And you use that when x is less than 0. This is the definition of that piecewise function. Just break it into a top and bottom piece. When you see the absolute value, you want to use this definition of it. All right. So when they say, what's the limit as x goes to 0 from the right, we're talking about x values that are bigger than 0. When x goes to 0 from the left, we're talking x values that are smaller than 0. So what that might mean for us is let's use the appropriate piece. X goes to 0 from the right. When x is greater than 0, we use this piece over here. We use the top piece. This is when x is bigger than 0, we're going to use this top piece. So just plug in 0 here for x. And you'll get 2 times 0 now, plus 7, which is the value 7. Okay. Now, for x being less than 0, you might say, well, when do I use the x being less than 0 piece? They tell you right here. You plug it in. You're going to use the bottom. So now you're going to plug in here again for x. You're going to plug in 0 like you did earlier here. You plugged in 0. But don't forget there's a negative there in front. Does it change anything? Well, not when you multiply it to 0. So this answer is also 7. So ladies and gentlemen, limit, left-handed limit's the right-handed limit, and it's 7. Okay, so the limit around 0 is the same thing, and that's really what you're seeing at this point here. on the curve here so you guys can see that. It's nice and continuous at that point. This is x is 0, y is 7, by the way. We can evaluate the function at 0 by using that top piece because it's defined for x being greater than or over here equal to 0. We didn't have to throw anything out because there's no fraction. So f of 0 is going to be 7, meaning there's no rational function. This is just nice polynomials here. And that's why if I go back over here and say, hey, guess what? F of 0 is also 7. Well, when we see this, we want to know that means the function f is nice and continuous at x equals 0 because the limit as x goes to 0, the function is the value of the function at 0. So the key again is because you've seen the absolute value right here, use the piecewise definition of it always. And that's going to actually, give you a way to do the analysis of this. But this is how you approach this question here, ladies and gentlemen. Write it as a piecewise function. So I'm going to call it an evening and send this to you guys and correct some of those typos. And I will see you guys later.